welcome to this course on gas turbines and jet engines. So, today is our final class, which is the lecture 60 and is the final class of the entire course. So, this final class of week 12. Okay. So, what we are going to do today, we are going to quickly go through some other experimental type of jet engines, and then we will have a quick comparison of the characteristics, and then compare the jet engines with rockets, because rocket is another major type of propulsion which is widely used, and then I will conclude with a outlook or with some discussion on what lies ahead in future. Okay. So, the concepts that will be covered today are introduction to other less used and proposed jet engines, introduction to other less used and proposed jet engines. So, this includes prop fan engine, and then there are some conceptual engines like turbo ramjet engine and turbo rocket engine, and then finally, we will conclude with comparison and summary and outlook. Okay. So, what is a prop fan engine? So, this is a concept which has been derived from the turboprop engine. So, we already know what is a turboprop engine, right. We know that, let me use this. We know that for turboprops, there is a core jet engine, and then a large propeller is there at the front, and the propeller gets rotated by the free turbine or a turbine which is being say rotated by using the combustion process, combustion products. Okay. So, these turboprops are generally designed, we have discussed that they are designed to fly at moderate or low speeds, okay, low Mach number such as Mach 0.5 or around that speed. Now, the issue with turboprops was that the way these are designed, if you go to very high speed, to get to very high speed, the blades at the edges of the blades of the turboprops will go to transonic or supersonic condition, which causes issues with the flight process, okay, with the airflow process. So, a modified design has been created or proposed and created with which is more like a unducted turbofan. So, shorter blades, more so less widely spaced blades, and it is like unducted turbofan. So, that it can rotate at high speed and generate thrust, but there is no duct present. Then as a result there is some noise, but it becomes more efficient. Okay. It means there is higher efficiency, it comes at the cost of some additional noise. So, how this was designed? So, this is typically the prop fan has fans like turbofans. So, that is why they are called as prop fan and not, but they behave like a propeller, and these are mounted on the back. Okay, although designs are there where it has been mounted at the front also, as you can see here at the bottom, but typically they have been designed in more cases to be mounted at the back, and they are again coupled to the shaft, where the shaft itself is getting rotated by the turbine. So, these propellers or the fans or prop fans are getting rotated by the turbine itself. All the other processes remain similar to that of turboprop, because there is inlet air, then there is the compression in the compressor, okay, then high pressure compression, then the expansion in the turbine, and then low pressure turbine which is running the fans or the unducted fans, you can say. So, this is an unducted type of engine, and there are some examples. So, this is the Antonov AN-70 aircraft, which is a heavy duty aircraft, lifting aircraft or cargo aircraft, which have been designed with these prop fan engines, as you can see, and there are two rotors on each engine, which generally rotate in opposite direction. Okay. So, contra rotating rotors are there. So, which is the reason which helps in running this even at very high speeds. Okay. Same thing also, but here we can see that the engine is at the back, not the engine, the fans are at the back and unducted. So, this is the GE prop fan engine, and this has been mounted on a MD McDonnell Douglas aircraft MD-81. Okay. So, all these are have been already have been applied, but not widely used till now. So, what is the advantage of prop fan? So, this was conceptualized as a very high efficiency engine. So, remember that this turboprop engines have very high efficiency and very good fuel economy. So, very low thrust specific fuel consumption, very low fuel consumption. So, that concept could be extended to near sonic speed like say Mach 0.9. So, that even large passenger aircrafts could be flown using this type of propeller type of engines or prop fan engines. Okay. So, that was the idea. So, this comes with higher efficiency in subsonic flight, but trades ducted noise shielding. So, it has more noise because no ducts are present, okay, but improves the fuel economy. So, saves lot of fuel. Okay. This was the idea behind prop fan. So, if I want to summarize all these points, so prop fan engines use large unducted multi-blade propellers. Okay. So, large unducted fans, these are driven by gas turbine similar to turboprop, and hypothetically they can go to very high propulsive efficiency depending on the fly speed. Of course, they can be designed at low speed also, high speed also. So, that is why they can have very good propulsive efficiency. They accelerate a very large mass of air like turboprops at low velocity. Okay. So, this is in between say turboprops and high bypass turbofans. It has combined features of both and thus and combined benefits of both the processes. Prop fans are also offer significant fuel saving. Okay. So, there is significant fuel say economy increase or lower thrust specific fuel consumption compared to standard turbofans at subsonic speed. They are the most efficient at high Mach numbers. So, 0.7, 0.8, 0.9. Okay. So, our designed to operate at higher speed as compared to turboprops. That is why these were designed initially. Some of the challenges and difficulties include high noise, okay, because there is no outer duct. So, the outer fan is rotating at very high speed and thus creates lot of noise because the airflow is at very high speed and there is no duct for shielding. Okay. Then the blade aerodynamics is means the blade design itself is very challenging because now you have to deal with very high speed flow. So, the blades have to be the generation or the development of the design and development of the blade is more difficult. Okay. Integrating with the airframe is also difficult. So, how it will be located on the airframe, where to locate it, that is also difficult, but this is still considered to be a strong candidate for future aircrafts, particularly for short and medium distance aircraft, okay, commercial aircraft like what turboprops are flying now, but to fly at a faster speed and slightly longer distances also, not for very long say intercontinental distances, but longer medium distance aircrafts. Okay. So, before going to the next part, we will have a quick comparison of the turboprop and turbofan engines. So, turboprop, turbofan, and we will also compare the prop fan. Okay. So, the main thrust source for turboprop is the propeller. Prop fan, the main thrust comes from the unducted fan. Okay. This is also like a propeller, but we have seen that it is designed differently. Turbofan, mainly high bypass turbofan, the propulsion comes from the bypass fan or the ducted fan basically, but there is contribution from the hot jet also. Okay. So, both are present. The bypass ratio, the equivalent bypass or effective bypass ratio is very high for turboprop. It is also very high for prop fans, both cases very high. For turbofans, it can be high for high bypass turbofan and it can be low also for military aircrafts, low bypass turbofans. So, this can vary depending on what design you want, what is the targeted aircraft velocity, cruise velocity. Typical cruise velocity Mach 0.4 to 0.6 for turboprop, Mach 0.7 to 0.8 or even 0.9 for prop fans, and Mach 0.75 to around 0.9 for turbofans. For high bypass turbofans, low bypass turbofans are generally designed for supersonic speed. Propulsive efficiency is highest at low speed. Propulsive efficiency for prop fan is very high at high subsonic speed, but turbofan also has good propulsive efficiency at high subsonic speed. Now, the important difference comes in fuel efficiency. Fuel efficiency is highest for the shortest routes for using turboprops. Okay. When the velocity is least, we get the best fuel efficiency. Prop fans have good fuel efficiency as compared to turbofans. Okay. Turbofans themselves have very good efficiency as compared to turbojet, but prop fans can hypothetically achieve even better fuel efficiency. Okay. Noise levels are moderate for turboprops. Noise levels are actually high, but because the rotor is rotating at a propeller is rotating at a lower speed, the resultant noise is not as high. It could have been high if the propeller would rotate faster. For prop fan, the noise is very high, because now the rotor is rotating very fast. Turbofans, particularly high bypass turbofans, are designed with one aspect also, means keeping into consideration is the noise. So, these are especially good for low noise requirements. So, they have very low noise relative to the other aircrafts. Okay. Low bypass aircrafts will have low bypass turbofans will have high noise. So, military aircrafts you might see that they have high noise. Mechanical complexity is moderate turboprops. Okay. So, they can be developed at relatively low cost and can be used for regional aircrafts. Turbofans, high bypass turbofans have high cost, but and high complexity, but the design is very mature now. It has been stabilized over lot of years of research. We have a very efficient and effective design. Okay. So, it is high, but now the research has matured in this area. Prop fan design will be very costly because of high complexity of the blades, high vibration and requirement of noise reduction. Till now not much research has occurred yet. So, it is still under consideration. Okay. Typical applications: regional aircrafts, utility aircrafts, future for turboprops, short to medium distance future aircrafts for prop fans, still not used till now, and commercial airlines for turbofans, okay, which is very widely used. This is the most widely used type of engine. On the right hand side, you can see a schematic comparison of turboprop at the top, turbofan at the middle, and prop fan at the bottom. Okay. So, now we will have a quick discussion on another type of engine. Just briefly we will touch upon this, which is a hypothetical concept, but one or two means prototypes have been built, or in one case one application or one design of engine has been used also in practical applications. This is known as turbo ramjet engine. So, we see that ramjets are very effective at high speed, whereas turbojets are more effective at relatively low speed relative to ramjets. Okay. Still high speed, but relative to ramjet. And the other issue is that ramjet cannot start from static condition, but turbojets can. So, the idea of a turbo ramjet is to combine both of these features, so that it operates like a turbine driven process. So, turbojet for moderate condition, and then at very high speed it acts like a ramjet. So, remember that afterburner works like a ramjet. So, it is more like there is a bypass of the air, similar to means to a section where there is a afterburner. So, like that. So, the air bypasses the turbine and directly like combustion and thrust is generated just by the ramming effect at high speed. So, quickly if I go through the features. So, this is an example of an actual engine J58 turbo ramjet, where it is tested at full afterburner condition. Okay. So, turbo ramjet is a combined cycle air breathing engine that operates as a turbojet at low speed and ramjet at high speed. So, it combines features of both. So, it avoids the drawbacks of both. So, it is also possible to use it at very low velocities, and it is also possible to use it at very high velocities where turbojet will not be able to generate thrust. At low Mach numbers, thrust is produced using compressor turbine system, enabling static thrust and takeoff capability. At high Mach number, it acts more like a ramjet, where the airflow is bypassed around the turbine, it does not go through the turbine, and the combustion occurs mainly in the ramjet duct. Okay. This enables efficient propulsion of over a very wide speed range, like going from 0 speed to a very high speed Mach 3, Mach 4, okay, unlike pure ramjets, which are only designed for high speed. So, what are the key challenges? So, these are types of hybrid vehicles or combined cycle vehicles. So, there are a lot of research again going on for combined cycle vehicles, and according to some research, so one of the major future direction of jet engine is combined cycle vehicles, where combination of turbojet and ramjet or turbojet, ramjet, scramjet can lead to a very wide operating envelope with high efficiency. Okay. But there are some challenges. One is how to transition from this turbojet operation to the ramjet when this transition is occurring, how to control that, the thermal management, because in pure ramjets there is no rotating part, here there are rotating parts, although they are separate and not directly in line with when the ramjet operation is occurring, but can still there is heat transfer which can lead to thermal management, and this is of course is more mechanically complex. This can be used for supersonic aircrafts where like no additional engine is needed for takeoff. So, the turbojet will take the vehicle from the subsonic condition to supersonic condition, and then for very high speed the ramjet takes over. Okay. So, turbo ramjets, in summary, turbo ramjet engines bridge the gap between turbine based propulsion, which we have studied extensively, and ramjet operation, which is also widely used. So, thus this combined cycle concept can enable sustained supersonic flight starting from takeoff itself. Okay. So, one final type of jet engine that we will quickly glance through also is a combined cycle type engine. So, this is known as turbo rocket engine. So, the concept is similar to turbo ramjet, but instead of having a ramjet here, a jet engine, okay, a turbojet engine is combined with a rocket, or a ramjet engine is combined with a rocket, and the idea is that when there is air present, the turbojet or the ramjet, so the air breathing engine will function. Air breathing engine has much higher efficiency as compared to rockets, because rocket need to carry their own oxidizers. So, their thrust to weight ratio is very poor as compared to jet engine. Okay. So, for the same speeds of course, and when the jet engine cannot be used, when the air density becomes too low, like near space or in space application, the rocket engine will take over. So, one area where this can be very beneficial is that during the takeoff part of space vehicles, the air breathing engines operate, and towards the end when it is going into deep space, the rocket engine starts operating and the jet engine stops. Okay. So, here you can see an experimental design of a NASA GTX concept turbo rocket. So, this is designed with hybrid propulsion system with a jet engine and rocket engine. There is a gas generator or a small rocket which produces high energy gases. So, this drives the turbine and powers also the compressor for air intake. Okay. Unlike conventional jets, this does not rely on atmospheric air. So, of course, because the rocket is present, the atmospheric oxygen is not necessary. Without it also this can operate, because oxidizer is there on board. The compressed air can be heated by the rocket exhaust and expanded through the nozzle to produce thrust, that is the thrust can be augmented like that. Turbo rockets can operate efficiently in thin air and at very high altitude, where normal jet engines will lose effectiveness, cannot operate because the amount of oxygen and air is very less. However, this is still an experimental and say conceptual stage. There are key challenges like the system will become too complex. Weight is an issue compared to simple jet engines, because now you are carrying the oxidizer, and efficiency will be lower as compared to pure jets at low altitude. Of course, this will have this is going to be designed for different application in mind, where space travel is also possible. Okay. So, in summary, this turbo rocket engine bridges the gap between air breathing and rocket propulsion engine. They will enable high altitude, very high altitude flight, high speed flight beyond the limits of conventional jet engine, but compared to pure rocket engine, they will have better efficiency. Okay. So, this completes all the different types of jet engines that I wanted to briefly discuss with you. So, we have seen so many different types of jet engines, starting with the widely used ones, turbojets, two types of turbofan, high bypass and low bypass, and again within turbofan the mixed say exhaust and unmixed exhaust, turboprops, ramjets, and then we have quickly glanced through scramjet. We have seen the working principle of pulse jet, pulse detonation engine, and finally today we have seen what is a prop fan engine, what is a turbo ramjet engine, and what is a turbo rocket engine. Okay. So, we will finish with a quick summary of these important types of jet engines that we have discussed the widely used types, and then what the future holds in terms of jet engines. Okay, what is the future direction of jet engines. So, if you see on the right hand side, we have a comparison of the different types of jet engines which have been developed or are being developed for wide usage. So, we can see that the operating speed ranges of the turboprop. So, starting from the lowest speed, then we go to high bypass turbofan. So, we have not considered the experimental or say conceptual vehicles here like prop fans, but the actual aircraft engines which are widely used. So, turboprops, high bypass turbofan, then going to even higher speed for low bypass turbofan, then higher speed range for turbojets. Okay. Although this can operate, all of this can operate at low speed, the efficiency will be poor. So, as accordingly the low speed end of the range is say selected. Then for ramjet, it cannot operate at low speed. So, it starts from high speed and can go to up to Mach 5, and then for the scramjet we have even larger say high velocity envelope going from say Mach 5 to Mach 10 or even beyond that. Okay. On the left hand side, you see a comparison between the specific impulse and the flight speed in terms of Mach number, and we see that turbofans are generally designed with high specific impulse, but are for lower Mach number. Turbofans with afterburner like those for military aircrafts can go to higher Mach number, but has lower specific impulse. Then ramjets will have even higher Mach number, but even lower specific impulse, and scramjets ultimately will have lower specific impulse as compared to the other types of jet engine, but in all cases the impulse is higher than that of rockets. Rockets are at the bottom, rockets have lower specific impulse, but of course theoretically they can travel at any Mach number going from 0 to extremely large Mach number like say 10 times the so 10 kilometer per second, which is like Mach 30 speed also rockets can fly, right. So, finally, a quick comparison with rockets. Why we are going into comparison with rockets? So, rockets are not jet engines, rockets are not part of jet engines. So, rockets are not air breathing engines, jet engines need air for the combustion to occur. Rockets carry their own oxidizer, so they do not need any air for their operation, okay. But they can carry this oxidizer in the form of solid or liquid also, whereas jet engines will use atmospheric gaseous air. Okay. Now, these are compared because there is some overlap along their application. So, for example, at high speed, high altitude, both jet engines can be used and rockets can be used, but jet engines will have higher efficiency, but it is restricted by the atmospheric envelope, whereas rocket can transition to outer space also. So, it is good to have a quick comparison between these two. So, for rocket engines, as I have already discussed, the oxidizer is carried by the rocket itself. So, rocket carries both the fuel and oxidizer in either solid form or liquid form, like oxygen and hydrogen. Oxygen will be the oxidizer, hydrogen will be the fuel. Jet engines use atmospheric air. So, no need to carry oxidizer, only the fuel is sufficient. Okay. So, which means that less mass is needed for generating thrust. Air requirement. So, rockets are more versatile, they do not need air, whereas jet engines need air. Operating environment, more versatile for rockets, atmosphere and space both are suitable, jet engines only atmosphere. Rockets also can generate static thrust, so they can go cover the entire speed range. Jet engines also can generate static thrust except ramjet and scramjet. Speed capabilities from subsonic and almost 0 velocity to orbital velocity like Mach 30, like 10 kilometer per second or higher, even higher speed. Jet engines also from subsonic speed, but it depends on the type of the jet engine. So, some jet engines can only fly at subsonic condition, some will fly at hypersonic condition, but are not suitable for subsonic condition like say scramjet engines. Okay, till now it has not been designed to go into even higher speed like say the high speed rockets used for space vehicles. Specific impulse in rockets is low, whereas for jet engines it is high. Fuel efficiency is very low for rockets. For jet engines it depends on the type of jet engine, going from very high for the turboprops or propeller based engines, then moderately high for turbofans and gradually decreasing towards the high speed vehicles. Typical applications, rockets are very widely used for all space vehicles, they are used for launching space vehicles, for missiles, many missiles these are used, for various spacecrafts these are used, okay. And there are many uses of rockets. Jet engines are also very widely used, but for aircrafts and for cruise missiles. There is a chance that in future both are combined together to get the benefit of both. So, they like what we have discussed as a turbo rocket engine. Okay. So, in summary of this comparison, rockets provide a completely rockets provide complete independence from air. So, they can work even at space. So, this enables space flight, while jet engines have the advantage that they are more efficient, far more efficient within the atmosphere, because they use ambient oxygen, but it comes at the cost of less versatility, they cannot work in space. Finally, we have come towards the end of our course. So, this is the last slide of the last proper slide of the course, and we will finish with a quick look at the future. Okay. So, what type of jet engines we can expect in future. Okay. So, the key area where lot of development work is going on is to improve the efficiency. Efficiency is the critical thing, and also lowering the emissions, which is another very important factor. So, this will drive future jet engines. So, I am just giving some pointers on what can be some future areas for jet engine research and jet engine development. So, this will drive future jet engine development, and for this advanced aerodynamics will be needed. Already lot of research goes on materials, the jet engine, turbine blade material, the say combustor material, liner material, nozzle material. So, all this and various cooling technologies to increase the combustion temperature. The other area we have to discuss today are ultra high bypass and open rotor concepts. Ultra high bypass as compared to turbofan and open rotors like prop fans to further reduce fuel burn. So, to get better fuel economy, but noise has to be reduced in these cases. Okay. Then combined cycles like we have seen turbo rockets or turbo ramjets. So, adaptive and variable cycle engines. So, either these are designed such that part of the flight occurs with one of the jet engine and part of it occurs with the other, or they operate both simultaneously using a hybrid mode. So, adaptive and variable cycle engines for efficient operation across wider speed. So, at lower speed, so for example, turboprop part is operating, gives high efficiency, and then at high speed when turboprops cannot operate, you go to turbojets or turbofan. Sustainable aviation fuel is another area. Okay. So, sustainable, like for example, hydrogen has very clean combustion. So, hydrogen, lot of research is going on towards hydrogen, usage of hydrogen as fuel. And finally, more advanced type of design techniques like digital design, CFD simulations, other types of say digital manufacturing, AI based control and continuous health monitoring. This can lead to improved performance, reliability and life cycle management. And in future also there are there are lot of thrust going on in the area of developing hypersonic aircrafts, hypersonic passenger aircrafts. So, that will be another key area for jet engine or combined jet and rocket engine. So, say low orbital space vehicles or high altitude atmospheric vehicles, okay, in those cases. So, in summary, the future of jet propulsion lies in higher efficiency, okay, wider speed envelope going from low speed to very high speed, lower emissions and adaptive engine architecture like combined cycles or combined engine architecture. You can see one of the conceptual figures which I have already previously shown for scramjet. So, this type of concepts are going to be vital in future for hypersonic vehicles or hypersonic passenger or military vehicles or say near space vehicles. So, with this we come to the end of our course. Today we have learned the concept of prop fan, turbo ramjet and turbo rocket engine, and then we have gone through some concluding remarks on jet engine and how this compare with rockets and what is the future of jet engine. So, I hope that this course has been very useful for all of you, and you have learned some important aspects of jet engine, and you will be using this knowledge in your future work. So, with that I wish you all the best, and I thank you for attending the class or attending the course, entire course. Thank you. So, these are the references. All the best. Thank you.